This is a video on Introduction to Dynamic Programming. In this video, we are going to learn the basic concepts of dynamic programming and the various methodologies to implement it. So, what is dynamic programming? It is an algorithmic paradigm that works by breaking a complex problem into sub-problems and stores the result so as to avoid recomputing. Let us understand this through an example. Suppose we are given 6 numbers as 2, 2, 3, 4, 2, 2. We are asked to find the sum of these numbers in groups of 2 starting from the left to right. That is, we are supposed to sum the numbers 2 and 2, 3 and 4, and then again 2 and 2. So what we do is we first compute the sum of 2 and 2 and get the result 4. We store this result in the computer's memory. So the sum of 2 and 2 is 4. Next we compute 3 and 4 and get a 7. We again store this in the memory as shown. Next we are supposed to sum 2 and 2 again. But we already have the result 4 in the memory. So we need not recompute it and we simply write 4 for this. Thus, this is the concept involved behind dynamic programming, that we divide the problem into sub-problems and store the result so as to avoid recomputing it. Another important fact concerning dynamic programming is its difference from divide and conquer approach. Divide and conquer is slightly a different technique in that we divide the problem into non-overlapping sub-problems and solve them independently, like in the algorithms of merge sort and quick sort. So suppose we are given a set of numbers 1, 4, 2, 3, 8 and 9. We are asked to sort this using the merge sort algorithm. So what we will do is first we divide into groups of 2. Then we will sort this group independently and this group independently again by implementing a recursive merge sort. So computation for this part and this part is totally independent of each other, whereas in dynamic programming, the problems are overlapping. And what we computed for a previous situation is used again and again for further situations. Now the big question is when to use DP or dynamic programming. If the given problem can be broken up into smaller sub-problems, and these smaller sub-problems can in turn be divided to still smaller ones, and if in this process you observe some overlapping sub-problems, then it is a very big hint for using dynamic programming. Dynamic programming is further categorized into two types. First one being the overlapping sub-problems category and the second one being the optimal substructure category. Let's discuss the overlapping sub-problems category first. Some recursive programs involve solving a problem again and again. Instead of solving them again and again, we store the results. Let us study the staircase problem, which is same as the Fibonacci series problem, to understand the overlapping sub-problems category. The problem says, how many ways are there to climb n steps if you can take 1 or 2 steps at a time? So we start at the ground step and we take either 1 step or 2 steps at a time. To reach the top of a staircase with n steps, there can be many ways. We can take all 1 steps to reach the top, or we can take all 2 steps to reach the top, or we can take a combination of 1s and 2s to reach the top. Our task is to find the number of ways in which we can reach the top. Next, let Tn be the number of ways to climb n steps. To implement dynamic programming, we first find the recursive equation for solving an overlapping subproblem. So in this example, what we do is we think of the last step we took to reach the top. So we are at the top and suppose we are here. So what would have been the last step to reach here? we either would have taken a one step or a two step to reach the top. Thus, our answer to Tn, that is the number of ways to climb n steps, is sum of the number of ways to climb n-1 steps plus the number of ways to climb n-2 steps. Since the staircase problem is also the Fibonacci recurrence, we provide a recursive solution to the Fibonacci series problem. In this C code, n represents the nth term of the Fibonacci series. Now suppose we are given to find the Fibonacci number of the fifth term. So we are to find the Fibonacci of 5. So how do we solve it using this procedure? The recursive procedure forms this recursive tree to solve the problem. That is, to find the Fibonacci of 5, we find the Fibonacci of 4 and 3. 4 is further divided into Fibonacci of 3 and 2, and so on. We here note that to find the Fibonacci of 5, we have to make a total of 15 recursive calls. We also note that while finding the Fibonacci of 4, we also compute the Fibonacci of 3. After performing this computation, we again compute the Fibonacci of 3 to calculate the Fibonacci of 5. All these computations made are redundant, and we would have skipped doing so if we would have stored the Fibonacci of 3. So this is where dynamic programming comes in. Next, we look at how to solve the problem using dynamic programming. We store the result by using either of the following two approaches, that is memoization or tabulation. So first we study the memoization approach to solve our problem. This approach fills up a table in top-down manner. Let us solve the problem of Fibonacci 5 using this solution. First what we do is we build a table. Then we pass the number 5 into our function. We also assume that the table is initialized to nil. Now if table of 5 is nil, which it is, we enter into this portion of our program. If n is less than or equal to 1, table of n is n. Else table of n is equal to Fibonacci of n-1 plus Fibonacci of n-2. Since n is 5, it is greater than 1. Hence we store table of 5 with sum of values returned from Fibonacci of 4 plus Fibonacci of 3. Now let us bring back the recursion tree to understand how this algorithm works. The Fibonacci of 1 and 0 is returned by this statement as 0 and 1 and stored in the table. Thus, at the index 0, a 0 gets stored in the table, and at the index 1, a 1 gets stored. Continuing with the solution, Fibonacci of 2 is next computed, which is equal to the sum of Fibonacci of 1 and Fibonacci of 0, and hence becomes equal to 1. Next, Fibonacci of 3 is computed using the stored value of Fibonacci of 2 in the table and the Fibonacci of 1. Thus, Fibonacci of 3 becomes equal to 2. Next, Fibonacci of 4 is computed from Fibonacci of 3 and Fibonacci of 2, which is already stored in the table and hence becomes equal to 3. Similarly, Fibonacci of 5 is computed as 5. This becomes our final answer. Thus, this forms the memoization technique for solving our problem. Next, we study the tabulation approach, which, unlike the memoization technique, is a bottom-up approach. Here also we build a table. We first initialize Fibonacci of 0 as 0 and Fibonacci of 1 as 1. For the rest of the values, we iterate through a loop as shown. Thus, Fibonacci of 2 becomes equal to Fibonacci of 0 plus Fibonacci of 1, which is equal to 1. Similarly, Fibonacci of 3 becomes equal to Fibonacci of 2 plus Fibonacci of 1, which is equal to 2. Fibonacci of 4 comes out to be equal to 3, and Fibonacci of 5 becomes equal to 5. This process continues till we reach n. Next, we study the second part of dynamic programming, that is the optimal substructure property. A problem has optimal substructure property if optimal solution of the given problem can be obtained by using optimal solutions of its subproblems. For example, consider the problem of finding shortest path between a source and destination node. This problem has following optimal substructure property. If a node X lies in the shortest path from a source node U to destination node V, then the shortest path from U to V is combination of shortest path from U to X and shortest path from X to V. For example, consider this diagram. Here the shortest path from U to V is the path from U to X, which is of weight 1, plus the path from X to V, which is of weight 2. Thus the total weight becomes equal to 3. The path from U to Y and Y to V is not the shortest path. The all-pair shortest path algorithms like Floyd-Warshall and Bellman-Ford are typical examples of dynamic programming.